This is video 3.2.1, and the goal here is to understand how to read, evaluate, and change to a logarithm. So we've talked about exponential functions and their uses, as well as the function e and how it can help us describe growth. So here's a particular situation that actually can be described using a natural logarithm. And I'll explain what a natural logarithm is in the next video, but just to help you understand where we're headed. On October 17, 1989, Northern California experienced an earthquake that measured 7.1 on the Richter scale. For each increase in 1 unit on the Richter scale, there's a tenfold increase in the intensity of an earthquake. So what they've learned is that this overall, once we know how much it's changed, we can describe how much the intensity will change. So once we know the unit on the Richter scale, we can understand the amount of growth that happened. So what we're going to look at, this is one thing that can be modeled using a natural log. Today we're going to look at just logarithms in general. The natural log corresponds directly to the unit e. So the natural logarithm would also help us understand a question like this. Suppose we were describing the world population by the function f of x, where x is the number of years after 1969. So notice that x is embedded within the exponent of e. And we wanted to know not what would happen after 20 years, but we want to know when would the population reach 10 billion. So we're looking for the opposite. So what we're really looking for is when will 10 billion, when will 10 billion, and now this is in millions, so we're talking about the following. When will this equal this? What x will make this true? Now we could guess and check different x values until we see what would make it 10,000 in this case, since it's y is in units of a million. But we want to know quickly. And so mathematicians created a model to do just that and so much more. So what they did was they created a model that would actually be the opposite of e. So it's going to be the inverse of the e function, and that's actually the natural log. So the big thing here is that we need the time needed to reach a certain level of growth. And that's in quotes because I took that directly from the article that you guys read about e. There's also an article on logarithms that will be an opportunity for some extra credit for you to read and comment on in the forum. So this is a quote directly from that. So we're looking for the opposite. We're now looking for the time needed to reach a certain growth rather than the opposite where we were looking for how much would it grow after a certain amount of time. So these are inverse operations, which you learned a lot about last year as well. So let's take a look at just what's the definition of a logarithm. So the definition of a logarithmic function, first of all, x has to be greater than 0. Notice where x is. And b is greater than 0. Notice where b is. This function says y equals the log of bx. B is a subscript, so it's lowered down below the log there. And x is the input value, so b will be some value. And we're only going to worry about x is greater than 0. This function, the way that you want to read this is that this is the logarithmic function with base b. The logarithmic function with base b. And here's how they're related. So if we were looking for the logarithmic function of base b, it's really asking the question, tell me if b was taken to the y power and you got the answer of x. So it's the opposite of the exponents. It's the opposite of these exponents. When we have y in the exponent, we have x instead. So what would be the power y such that I got the answer of x? So here's a couple of ideas on how to read this so that this makes more sense to you. I think the number one way to make sense of this is to show you some problems that will allow you to kind of see what's happening here. So let's take a look at this example here. So we're going to change the following from log form to exponential form or vice versa. So let's read this first one. This first one, 2 equals log base 5x. That is saying 5, that's the base of my exponent. So just like it's described here, b is the base, y is the power, x is the output answer. So we're saying 5 to the second power in this case equals x. So this tells me that x must be 25. 5 to some power 2 equals x. Okay, so the value here, the y value, is the exponent. The b value is the base of the exponent. And the x value is the result, the answer after you take it to that power. So let's try it again here. Now we have log base b to the third power gives you 64. So b to the third power equals 64. These are equivalent expressions that I've written here in green. These are written in exponential form, and these are in logarithmic form. Now remember, there is a key on your calculator that allows you to take the log of a certain value from a certain base. So we will be using that to help us calculate some of these that are harder to see the actual answers. Hopefully that you're seeing, though, that b would equal 4 in this case, because 4 to the third power is 64, and x would equal 25 in this case. Let's take a look at this next one. Now we want to switch it around. So now we want to write it as a log. Let's see, log. We first look for the base. The base of the exponent is 12. The power is 2, so that's the result. The exponent is 2 of x. So 12 to some power 2 equals x. Now we look here. So log base b to the third power equals 8. So again, this is your exponent. This is the base of your exponent, and this is the result. Okay, so this is just something you're going to have to memorize, how it's set up. Okay, but it does matter the base, so there's that extra subscript that you see in all these problems here. That's an important piece to these problems. This is what you'll be doing for your first assignment in class. Let's take a look at one more thing that you'll have to be able to do. One more objective is that you need to be able to evaluate the log. So this is asking, so we have to first figure out what it's asking. Yes, we can use our calculators, but for now we're going to use kind of just what we know about exponents and such. So we see log base 2, 16. So that tells me that 2 is the base. I don't know what power it was taken to because that's what I'm looking for. But I know the answer gives me 16. 2 to some power gives me an answer of 16. Let's see. So 2 to the second, 2 to the third, it must be 2 to the fourth. 2 to the fourth power equals 16. Therefore, x equals 4. Excuse me. X equals 4. And that's what it means to evaluate the log. Because we solved for x here. X equals 4, so 4 is the same as log base 2, 16. Okay, so again, let's try this next one. 3 to some power equals 9. 3 to some power equals 9. 3 to the second equals 9. Therefore, x equals 2. Log base 3 to 9 equals 2. And then let's see, 25. 25 to some power equals 5. 25 to some power equals 5. This one's a little bit trickier. So the answer got smaller. So whenever the answer gets smaller, what does that mean about our exponent? That's something that we should have kind of reviewed in the last section. 25 to some power equals 5. Here's one strategy to help you solve this. I know that I can change the 5 to 25, which would give me the same base here. So let's see, if I square both sides, which is a legal move because we're working all with positive numbers here. That would be not a legal move if we were working with any negatives. 25x squared equals 25. I can use my understanding of exponents here to rewrite this as 25 to the 2x. because when I'm taking a power of exponents, I multiply the two powers. 2 times x equals 25. And 25 on the right-hand side is to the first power. So 2x has to equal 1. Because these powers have to be the same. I have the same number of 25s on both sides. So that means x is 1/2. Think about what you remember about fractional exponents. Fractional exponents are equivalent to, is how we work with square roots even. The square root of 25 is 5, and that means that 25 to the 1/2 is 5. If you remember 1/2 meaning because we're taking it to the square root, meaning something squared equals 5, that's why we do 1/2 because of the 2. The fact that 5 squared equals 25. So that's just one review of your fractional exponents, but this is another way to solve that. We'll talk about how to use your calculator in class once it becomes valuable. But for now, I want you to give these next checkpoints a try. See if you can write the following equations in exponential form, the equations in logarithmic form, and evaluate the different values here. So do your best, bring your questions into class, and we'll go over more of the difficult ones like you saw in that last example.